a lot of people know me, but I'm Lars Jorgensen. I'm the director of genome sequencing informatics in my day job. But before I got into bioinformatics, I did computer science in Copenhagen, and I have a Danish family. So that's kind of where the link comes to this system. So DASK stands for Dansk Aritmetisk Sequence Calculator. It's the first electronic computer in Denmark. The English translation is Danish Arithmetic Sequence Calculator, which is because it's arithmetic and it does things in sequence. It was based on a Swedish system called DASK, which I'll talk a little bit more about later. These are two pictures of the system. So the picture on the left shows the part of the casing which holds most of the vacuum tubes. But on the bottom left side, you can see the magnetic drum, which was one of the storage mechanisms it used. On the right is shown in action in a house where it was built. And you can see the main control panel as well as keyboard input. So the reason I'm talking about this is because I inherited one of the vacuum tubes from this computer, so I have it at home. I decided to take a picture of it because I didn't want to break it. So it lives in this wooden case, which in Danish says vacuum tube from the computer DASK, which was from 1957 to 1967. And the other day I was curious about what tube it actually was, and it turns out it's a Philips triode tube, and you can buy them for about 30 euros each. So if I want to try and recreate this machine, in theory, I guess I could if I can find enough of them. So as I said, it started as based on a Swedish system. So after the Second World War, Sweden had gotten through a lot more unscathed than Denmark. And so in 1948, Sweden created Mathematiks Maskinsnämnden, which translates to the Mathematics Machine Commission, to explore what the need was for electronic or just even mechanical computation machines for research and defense in Sweden. And so in 1950, the working group created the first system, which was called BARC, which was a binary automatic relay calculator. So it wasn't really an electronic computer, but more of a electric calculator. Then two kind of parallel initiatives started. DASK started before, but in 1952, the Department of Physics at Lund University started construction of a system called SMIL, Ciphermaschine i Lund, which basically means the cipher machine in Lund. But before it completed, DASK finished construction, which is Bina Elektronisk Sekvens Kalkulator. Those very inventive names of these machines, which basically means the binary electronic sequence calculator. And by the time that was done, they decommissioned BARC because it was no longer useful at that point. So in Denmark, things moved a bit slower. So in 1946, the Academy for Science created the Calculator Machine Committee, which was tasked with exploring the need for mathematics machines for research in Denmark. They ended up creating a mechanical differential calculator, but held off a bit about creating an electronic computer because they wanted to see where things were going. And for pragmatic reasons, in 1952, they asked the Swedish government and their counterpart if they'd be allowed to build a replica or modified version of DASK, and the Swedish government approved and gave them access to the blueprints and know-how. This is research, so funding was always a problem. A collaboration was created between the Armed Forces Research Council and the Calculator Machine Commission, which created the Danish Institute for Mathematics Machines, which I'll come back to in a bit. And I think that's where my vacuum tube kind of stems from, because my granddad was in the logistics of the army, and the army was interested in it for calculating ballistic trajectories. So if you need to shoot a gun over the horizon, you need to know the air, wind, temperature at altitude, and it's not just putting an angle and then you'll hit. So historically they had big tables which people had manually calculated, but they wanted to be able to calculate those faster, as well as other types of research and logistics. So via that, they were allocated match funding of 900,000 Danish from the Marshall Plan funds, which was the US funds to rebuild Europe after the war. So that all came together in 1955 and construction started. And then in September of 1957, the machine was unveiled to the public and was completed. It was, after that, it was mostly used for research and defense, but one of the bigger kind of publicity things it was used for, which was common for early computers, was it was used to try and predict the election as a result of the 1960 Danish parliamentary election. So, as I said, it was housed at the Danish Institute for Mathematics Machines, which is in Danish called Regnecentralen, which roughly calculates to Calculation Central, which was based in a detached house in downtown Copenhagen. It was created in 1958, and it stayed around for a very long time. So the machine on the left is called a Piccolino, which is a very common kind of machine they built, Z80 based, which was used in a lot of schools. So it in very many ways mirrors the influence the BBC Micro had in the UK. On the right is a picture of Gear, which is the machine which followed on after DASK, as well as the president of the institute, together with Peter Nauer, which is the only Danish person who has received the Turing Award. He's most known for, if you ever written a context-free grammar, then you've most likely used BNF, which is Backus-Nauer form, and so he's the N in that, as well as he contributed to a lot of other work. I'll come back later, but he spent some time in Cambridge, but spent most of his time working on DASK and all the later machines. So this is a small kind of overview of what the timeline looked like for early computers from a Scandinavian point of view. So 1944, you have Harvard Mark I, and then things kind of branch off mainly in EDVAC and IAS designs. So IAS stands for the Institute of Advanced Science. And John von Neumann was very involved in that. So if anyone ever heard of the von Neumann architecture, that's kind of where it comes from. So he helped develop what we today know as a modern computer. And as well as you have the Manchester Mark I, which got commercialized into the Ferretti Mark I, which was the first commercial computer. So it beat the UNIVAC, which was the first US commercial computer to market. And then from a Scandinavian point of view, you can see DASK is kind of a logical descendant of IAS, and DASK is from that, as well as the Manchester Mark I. So Sweden built a machine, Denmark built a similar machine based on the design of Sweden, but Norway just decided they couldn't, they just went out and bought a commercial machine. So they bought the Ferranti Mercury, which is was a commercial British machine, which, if my Wikipedia skills are good, is also the first computer CERN got in. So those were kind of the three main machines you had in Scandinavia. And you have a bit, I don't know if it's easy to see, but there's a dotted line, and that indicates which machines had index registries. So that was one of the additions to DASK. So they took that idea from the Manchester Mark I of having indexes to enable easier jumps. I'll come back and explain a bit more about what they do later. So it combined those two. And then there's another subdivision which contains the BSM-1, IBM 740, and Ferranti Mercury, and that's that they had native floating point. So DASK had fixed floating point, but it had fixed point arithmetics, but it didn't have floating point. You could do floating point on it, but you had to do it in software. So this is probably repeat for most people, but I thought I'd give a bit of background. So most modern computers and all computers are stored program computers. So your program is data. You normally use a high-level language. You write your program in that. You put that through a compiler, which turns it into assembly language, which has operators and operands. So for example, the shorthand here of add means add immediate. So it adds the value of registry to a constant. So and here in this example, we would add 10 to a registry, and thereby another way of setting the value. And then you have this branching mechanism. So if I just quickly walk through it, it does the same as the thing above. You add 10 to one variable, you add 0 to another variable, and then you go into a loop where for one of the variables you add 1, for the other one you subtract 1. And then there's a conditional branch here. A branch is greater than 0, which says if the value in RG1 is bigger than 0, then go around again, and then at the end store it to memory. Because most machines are designed this way that you fetch your instructions from disk or from memory as data. They get decoded, so each of these names represented by a bit pattern, which then raises different lines in the CPU and makes it do different things. Or the values go into registers, which is just very fast memory, which is on the CPU. And then the heart of the computer is what's called the ALU, which is the arithmetic logical unit. So it can do add, subtract, multiply, and division, and bit shifting. So that's kind of the heart of the machine. So a simple way of describing most computers is just that it's a pocket calculator that, based on a number, can decide what it wants to do next. And then if you add memory to that, then you can write values in and out. So those are kind of the fundamental elements of a computer, and I'll come back and hopefully show where each of those components are in the DASK design. And then as a side note, it's even though this is kind of the fundamental design, today's CPUs are extremely complex. So even if you take a simple computer like a Raspberry Pi, it still has a highly complex CPU on it. So even if you tried to do simple things, it's probably doing something else behind the inside the chip than you think it is. So a lot of CPUs these days schedule instructions for you and will do things out of order. They do pipelining, so there are multiple things going on at the same time. So they're much more involved, and they're not simple computers. They're just basic computers. So, and that's what kind of, apart from the historic link, appeals to me about older hardware, is that it's easy to understand, it's easy to get your head around. And then there's just a small rant about Intel instruction sets, that if you're working with an ARM or a MIPS, it kind of makes sense, but if you go onto other platforms, then you have very strange instructions. You have instructions that write to stack, and it's just impossible to. You need a lot of knowledge and experience to do something, and people spend years on compilers and do it better. So going back to the basics is kind of nice sometimes. So in terms of hardware, so DASK consisted of 2,500 vacuum tubes, 15 crystal diodes. It had a variable step up of power, so it took 105, 106, and 220 volts. Everything in Denmark, like the rest of Europe, is 220, 60 hertz. And the idea there is that you would power it up and run a test. So if any components were going to fail, they would fail when you powered it up instead of when you were running it. So you kind of overcharged it a bit and then brought it down again. And internally, different things run at different voltage, which I'll come back and show some of the crazy voltages things run at. But the lowest was kind of down to 6.3 volts, which even by today's standards is massive. You can't even get that out of USB. And this is a number based on DASK, but the normal power consumption when the machine was running was about 15 kilowatts. I don't know if it had a global clock. I think it must have, but the only thing I could find out is that it had a 143 kilohertz pulse generator. So, and just a caveat, everything I present here is based on me interpreting, reading very old documents, so there might be some misinterpretations. For external units, it had the magnetic drum storage, it had typewriter output, and could also accept keyboard inputs. But the main way of driving it was using 5-hole telex strips, and it had a reader and a perforator. So you could get it to write telex strips, turn those around, and then read the content back in again if you wanted. And later on its life cycle, as like IBM punch cards became more prevalent, a punch card reader was added. So in terms of specs, it had 1024 40-bit words, so it was a 40-bit machine, which was true for IaaS and DASK and the other machines. I don't know when that changed, when the more classical 16, 32, and 8 showed up, but back then it seemed like a lot of machines were running on 40 bits. Most of the time you would work, so that was known as a word, and then most of the time you'd work on half words, so you would use 20 bits. It had a 5 microsecond read-write main memory, and then the magnetic drum could hold 8K or 8K of 48-bit words, but it was serially attached. So if you were going to write 32 words, which was one rotation, it was a 20 millisecond operation. And which, from what I read, kind of equates to some bits per millimeter. So it was fairly low density. A fun difference between BESK and DASK was that DASK used 32 by 32 grid ferrite core memory, which is the thing in the middle. When I read about this, it turned out at some point BESK used cathode tube memory, which I'd never heard about before. So basically, it's like storing information in your television, and apparently it wasn't very reliable, but so you could use cathode tubes to store data. But this memory was much more simple. You can see it's a grid of X and Y lines. So one line individually is not enough to flip the magnetic orientation. So, but if you combine two currents, it will flip the current. So that means even if the Y line is high, all those things on there will not be affected unless the XY line is high. And that's for writing. And then the thing that kind of zigzags through is for reading. So you would bring that up high, and then you can read output on the X and the Y axis. The drum, it was running at 3000 RPM. It had 256 read heads. And one of the complications was that a write required 150 volts and a read was 50 millivolts. So they describe a bit about how it's a bit complicated to have that range of current going through a thing, but using an amplifier, they managed to get the sensing to work. And then in terms of CPU registers, it has 3 registers in its ALU, and it has 7 registers in the control unit, which is pretty much the rest of the computer. And the diagram on the left is mostly for curiosity, but it's what an individual registry cell would look like. And I don't know if I've used people, but these things, each of these things are basically a vacuum tube, and each of these is a resistor. And it's compared to modern computers, so this is minus 200 volts, plus 150 volts, and 120 kilo ohms. So it's not a computer you want to stick your finger into. But this was then replicated a number of times for each bit to create a 40-bit register. So this is an overview of what the whole machine itself looks like. So just some quick translation. So this is the decoding matrix for translating an address into a specific location in the working memory. And like I said before, the working memory has 1024 40 bits whole words or 248 half words. And it can read a whole word in parallel, so it can read 48 bits out directly. And this unit decides if you're reading half or whole words from a specific location. This box over here is the magnetic drum storage, which is 256 channels, each with 32 words on it. And it will read one channel serially at the time, so you're reading one bit in at the time. This down here is the closer you get to the ALU. This is the accumulator registry, so if you're doing addition, you would store a value here. The next time you get another value, you add it to the value which is currently there. There's the multiplier registry. So the way you would do 2 times 3 is to do 2 plus 2 plus 2 plus 2. And the multiplier remainder registry. So this is a normal calculation method. This down here is the operator instruction registry, which will contain your instruction. Down here called BR is a binary counter. So there's a register you can use as a counting method. There's the control registry, which works to affect the address registry, which is just above it, which is what points to what cell you're going to access. And then you have and there's an adder between, because these three up here are index registries. So the way an index normally works is you can shift your computation off by a certain point. So instead of giving the absolute address, you can just give the index plus an offset. Or you can use it if you're working in a piece of code, call a subroutine, but you want to get back here, you can store it there and then use it in your return call. So they're called 3, 5, and 7, but generally they're referred to as B, C, and D. So data would come in here and populate the operator and the address registry combined with the control registry, and then that would invoke whatever action was programmed for that instruction. So as you can see, it's a fairly simple machine, so it has relatively limited. It has 32 instructions, and about half of those are just arithmetic instructions. So this is what the instruction format looks like. So it's a 20-bit string. Bit 1 to 11 will normally be referred to like a cell address or other things, but normally it would be a memory address. Bits 0 and 12 get combined into the equivalent of 1, 2, 3, 4, but referred to as A, B, C, and D. And that's a convenience since it usually be used as a modifier on the jump instructions. So it's convenient because the jump registers are IR, B, C, and D. Then you have B, C, and D, so it's easy to see which jump register you're using when you're using the jump instruction. And then the last 13 to 19 is used to encode what operation you're using. So 0, 1, 2, 3. And the way this works is that the first bit is written, when you write your program out, is written in decimal form. The next bit is written as A, B, C, or D. And then the last bit is written as hexadecimal, which was called Say-decimal at this time. I have no clue. And that means a bit string like this will end up looking something like this. And this is how your instructions are going to look. So it's the equivalent of the ADI something I was on my previous slide. On top of this system, there's a modifier. So the two highest bits, or what do you want to call it, 13 and 14 in the instruction are modifiers, and they're referred to as V40 and V20. And so you can use them to create 20, 40, or 60. and then you add that to the instruction name. So there's a small example over here which should hopefully make it a bit more easy to understand. So in this example, we have 4 variables, x, y, and z, and v. X is stored in the left. I'm just going to jump back a bit. This is the memory layout of the machine. So you have 1024 40-bit words divided in 2, where the even cells are on the left side and the uneven cells on the right side. So it goes 1, 2, 3, 4, 5, 6, 7. So if you know if an address is even, you know you're referring to the left cell, and if it's uneven, you're referring to the right cell, unless you're referring to the whole cell. So if you're referring to 100, but with an instruction which uses the whole cell, which you define using these operators, then you if you're taking a half or whole cell, you're taking that part. So I'll try and walk through this slowly. So this is the first instruction in this program, which says 100A60. So it means take address 100, so position 100 in memory, modifier A, which is basically nothing, which is 0, 0, and then 60, which is 0 plus 40 plus 20. So it's 0 is addition. So all the 3 instructions, or all the 4 instructions in this program are additions, but this is using a modifier which tells it to take the left value of, so take whatever is stored in here, not in all of it, and put it into the left side of the accumulator registry. So it basically means now we have X, and the reason it's 60 and not 20 is because the other side effect is that it zeroes the accumulator registry before it stores something in there. So you start from fresh. Whereas the next thing does the same, but it now is slightly different because it doesn't zero the registry before, and then so we end up with first X, and then we end up with X plus Y, and then the next 2 instructions just takes the full 40-bit word and adds it to the accumulator registry. So in the end, we end up with X, Y, Z, and V in the accumulator registry. We don't really do anything with it; it just stays there. And then the next instruction is a special instruction, which means stop, which means the machine stops, but it takes 5 as an argument, which programs the program counter. So the next time you power on the machine, you'll start from position 5 in memory, which is basically the next line down. So any questions to that? So it's so just to summarize, so all of these over here are just referring to memory addresses. The ones in the middle don't really do something because they're 0. And all of these 4 are actually the same, but they're just a modifier because either you want to do something to the accumulator register before, or you're adding a 0. So this is the whole overview of commands which are available for the machine. So they're in Danish anyway, so it doesn't matter if you can't read them. These 4 up here are subtractions and addition operations, so 1, 0 to 6, with slightly different, some of them stored to multiple locations, and the last one adds something up and then writes it to a location. One thing that was confusing about reading this manual was that they don't say read and write, they say read to and from. So reading from is read, reading to is write. So you need to get your head around that before you try and figure out what's going on. The next ones are just moving memory around, so moving the multiplier registry into the accumulator registry, moving the value of the accumulator registry to a cell. So the most commonly used registries are RA and AS. So AS is the address registry, basically tells you where you're on the program. and accumulator registry is just where you do all your computation. Then we have multiplication, division, shift left, shift right, signed, normalize, and shift left unsigned. So these are kind of your normal math ALU operations. Then we have 4 jump instructions. So you have unconditional jump, branch on it basically branch if greater than or less than 0. So jump on sign. Branch on overflow, and branch using an index. So basically, if you were doing your end of your subject key and you wanted to jump back, you would probably use that. And then 2 instructions for writing the value of a index registry to memory or getting it back again. So if you were doing like multiple calls and you wanted to store your return address in memory, so say you do 4 calls deep. So you call a function, you push your variables onto the memory, you store your return address, and then you do the same thing again. Then if you run out of index registries, you can store them in memory so you can get them back if you want to. Or if you have more than 4 places you want to be able to jump to, then you can store it in memory. And a small thing I forgot to say, this C parentheses notation means content of. So, which most of the time it's what you're referring to. You're not referring to the registry, you're referring to the content of the registry. And then these down here are I/O operations, which I'll come back to later. And down here you can see the table of, so each operation has a modifier type, and then this table tells you, depending on what your V20 and V40 were, this is how they all behave. So that this is where the set the accumulated to 0 before doing the addition, or don't change the accumulated registry before setting the value. So there's a lot of, even though it's a simple instruction set, there's quite a lot of modifications that can happen. So here's a bit more complicated program. So basically what it does, it has 4 values, x, y, u, and v, stored in 50, 51, 52, and 53. It will subtract y from x. If the result of that is greater or equal to 0, then it will subtract u, and if it's less, it will add v. So it's a fairly simple do this, if, else kind of thing. So it starts by zeroing the accumulated registry and storing the value of x in it. Then it uses the left version of subtract to subtract y from x. And then this is a jump instruction. So it says go to 5 if the accumulated registry is greater or equal to 0, which contains x minus y. So if this is true, it will jump to 5. If not, it will continue to the next line, which is add v to the content of the accumulated registry. So you get x minus y plus v. And then the next instruction is an unconditional jump saying no matter what, just go to 6. And if we up here had chosen to jump to 5, then instead of adding v, we'll subtract u, and independent of which branch we took, we'll end up down in this row, which says write the value of the accumulated registry to location 54. And then once again we stop and put 8 into the next start address. So that's short walkthrough of 2 of the programs that were available in this system. Hopefully everyone understood. So when you were developing for this machine, you didn't really have like Eclipse. So they had like 2 things they recommended. There's a whole chapter on making these flowcharts. So you would draw your program using these flowcharts, and then code it afterwards. So this is your entry point. So your program starts and you say, if R is 0, stop. If it's not, then subtract 1 from R and store it in the R counter. And then it does the same for S. And then it'll go into different branches. So it was just a fun historic thing to read about their explanation of how do you program, and you should draw all these flowcharts on how to easily understand your code. The other way was to use their standard libraries, which would contain things like square root. And it says, so nib, which is an abbreviation, in March, 15th of March, 1957, coded it, and then on the 8th of October, 1957, someone else loaded it into the machine, and then there's a publication date. So, but there's a bunch of these more and more complex methods, and basically all these say is, what's your entry point, what's your exit point, what should the conditions be when entering into this function, and then that's that your variable will be in the accumulator registry. And when you're done, the square root will be in the accumulator registry and the multiplicator registry. It will maximum take 22 instructions. And this is the minimum and the maximum runtime. I haven't been able to figure out what AT is, but it must be some form of cycle-related thing. And then there's the length of the code, if there's any subroutines, which there isn't in any of these, and it starts at an even address, and it will work through the memory in sequence. And it's got one constant, which is stored in 2042, which it uses to calculate square root. So the system also had an operating system, or it had what was called normal state 1, which which was kind of the core operating system, but then it also had a bunch of additional helper routines called control programs. But the operating as such lived in the memory as space from 1984, which I don't know if they picked for a specific reason, to 2046. So they say, like, don't touch this. And they explain that one of the main programs in there is a program for loading program. And don't try and understand how that problem works. Just assume it's there. Because I think someone had to manually type that into the computer. But it's a program that sets up the machine and is at a point where it will start reading a telex strip with your program on it. And below these 2 pages is the operating system. So it's fairly sparse. And additional on top of that, there were some conventions about how to use the memory space. So this part just says available for reading data from external units and for the control program. And this is for writing data to the external unit, mainly the magnetic drum, and for control programs. So running it, as I said, you use telex tapes, and they were around before this computer. So they were used, I assume most people know telex, but it's basically a way of encoding characters into a strip, and then you can send that, and then you stick it into the machine on the other end, and it will print it out. So you could have hexadecimal characters, so you have 0 to F here, depending on these hole patterns. And then, like we saw before, most of the instructions will be some address, one of these A, B, C, and D, and then the operation. And then you can encode that on tape using this. So this is the punch tape encoding of this instruction. So you just went along like that. This is the magnetic drum, which was the external unit. And then if you wanted to access it, these were the instructions. So the first one is read a hexadecimal character from the strip and put it into memory. and the next one is output a character, or next to outputting a number, outputting a character. Choose external unit, read from the external unit, seek and write to the external unit. And the external unit could be the perforator, the magnetic drum, or the typewriter. And because of that, you have a number of special characters. So you have stop, start, dot, dash, plus, minus, tab, space, and carriage return. I don't know if they had space and tab debates back then, but so this is the control panel for the machine, and the round things without anything in them are bulbs. The black thing, the circles with black in them are buttons. These are toggle switches, and these are keys. So each of these lines, so there's a grid system I might refer to. So there's 1 to 45 at the top, and then B to K. But so A is a visual representation of what's currently in the MD registry. So when the machine ran, you could see the exact value of what was contained in the registry. And then on the sides, you could zero parts, like the left or the right side of the registry. So if you wanted to zero something, you could just press this button and it will zero out everything in the registry. So this is multiplicator and the multiplicand and multiplicator registry. I don't know if I translated those correctly. The next one down is the address registry. No, the accumulator registry. And in addition to be able to zero that, it also has buttons so you could program. So if you wanted to put a specific value into the accumulator, you could use these buttons to do that. And which is, I think, how they put the initial program in there, was like typing it in binary, loading one instruction, typing next instruction, load it in. The next one down is the address registry and the operator registry, the control registry, and the binary counter over here. And then you have the index registries, which are just, you can't zero those, but they're just displayed. Then these buttons are, this is the speed control. So gang means walk in Danish, so that would just be normal running. Trin means step, so it would be one operation at a time. So every time you press start, it would go one operation. And then you had the next up is variable speed, which would use the button next to it to control how quickly the machine executed. The thing here in the middle is a speaker, and you could connect that to a specific registry. And they said a good way of debugging was to listen to the sound of the content of the registry, and then by listening to the rhythm of how the machine was running, the sound it was generating, you could see if the execution was going as expected. Here you can disable jump instruction 56, and this is a function for disabling the jump registries, but they said they removed the button so people couldn't use it, because if you're running a normal program and you disable jump instructions, weird things will happen. So they probably regretted putting it on, so they just took it away. This is the output selector. So you can either go to typewriter and perforator, typewriter, or nothing at all. And that would decide what things go out. And then this is start, stop. There is something about control label programming, which I didn't have time to get my head around, which involved the magnetic drum. So that's what this controls. So if you're going to start this, you would zero the registries, insert this as an initial instruction, just hit go, and then it would start reading the tape. That's how you control it. There is an emulator for this machine, but unfortunately it's quite unstable and uses motif libraries, or like old X11 libraries. So I tried running it, but it keeps crashing, so I'm going to try and get that running in the future. So, like I said before, Peter Nauer was one of the key people who worked on this, and of course, 5 minutes into this, people are programmers, they want to do things more efficiently. So people started looking into what's called autocodes, which were kind of a precursor to a compiler. So it didn't have a parser, it didn't have any of things like that, but it was just a more efficient shorthand than using the normal programming. DASK had two languages called FA5 and AlphaCode, and the Norwegian machine had Mac. So this is a Scandinavian biased view or Nordic biased view of what happened in terms of compilers, but you have other languages in here as well. Because the Danish machine had index registries, and Peter Nauer had spent some time in Cambridge, they actually started developing a fairly high-level language for it, which was Algol 60, which initially was started by Bacchus, and developed that. So from a programmatic view, I think DASK was a much more friendly machine than the other ones. And so the kind of things from this list that kind of survived are probably Fortran and then Algol, which in turn inspired Simula, which inspired C++, and from there on out. And it was as part of this, Nauer came up with BNF because they designed the context grammar to describe Algol 60, and continued to go on and do a lot of other programming related work. So what was the difference between what if Fortran had won kind of thing? Fortran was a very simple language, but it apparently had a very advanced compiler. It did Monte Carlo simulations inside it to try and find the best code. But then you're starting to see things like you have infix operators, you have parentheses, so now you can actually say x plus y divided by z. So it's becoming a bit more like the program language we know and care. And Algol 60 is pretty much has a lot of the normal things. You can do function calls, you had nested scope, you can declare types and a lot of other things. So at that point, you're pretty much up at a modern language. So I think I'll wrap it up there. So most of the information I have is from the Danish Computer Museum, which is a volunteer organization, which have been friendly enough to scan all the documentation on this computer I could read through to try and understand how it worked and how it's supposed to be used. As well as there's been a number of symposiums on Nordic computer to try and capture the history of computing. And as I said, some of the data points are Wikipedia and Google, so this is not a hard historic reference, but hopefully I made it as accurate as I could.